Mapping the AI models on hardware faces significant challenges due to high computation and energy requirements. So in this video, I'm going to explain shared layers methodology, which is an efficient way of implementing CNN models on the hardware. Later in this video, we will also see that how can we extend this shared layers approach to have a reconfigurable CNN accelerators, which can operate in several different operating modes, such as fault-tolerant, high performance, and de-stress mode. So this video is going to be an academic style in-depth video. Let's get into it. Hi everyone, my name is Rizwan Tarek and welcome back to another video. In this video, we are going to be discussing shared layers methodology, and we will apply this methodology on two different CNN architectures. First is going to be the fused architecture, and another one would be a branched CNN architecture, and we'll see how it works. This is going to be a very in-depth video in which we'll talk about the fundamental concept of shared layers, how we are creating fused and branch models, and then how are we implementing it. We will discuss the workflow of creating these two models, and then in the end, we will discuss in-depth implementation results, which consist of power consumption, hardware resource utilization, accuracy, and model compression, quantization and pruning, all of those things. So yeah, let's get started. This work is basically part of my PhD, and this is published in this paper towards Reconfigurable CNN accelerator for FPGA implementation. If you Google this title, you will be able to find the paper as well. But yeah, all the things that we are discussing, it's basically part of this paper. So this is the outline that we are going to be discussing. We will see like what are the challenges that we are facing right now, and there's going to be two major takeaways. First is how we are implementing the shared layers approach, and then how we are extending this approach to create a reconfigurable CNN accelerator. And yeah, of course, we will discuss the workflow, how to sort of generate or how to implement these things. And then we will also discuss the implementation results. And in the end, we will also see like how we are extending this work. So yeah, let's start with the challenges. What are the challenges that we are facing right now? So eventually, all the AI models will run on the hardware. But hardware faces a lot of challenges, and one of them is the varying AI application requirements. So the number of sensors are continuously increasing, and with that, the new data is being collected every day. This would mean now you have new accuracy, new computation, and new latency requirements after every couple of months. And this change in the AI requirements directly impacts the hardware area utilization, which also impacts the power consumption as well. You can also have a look at it. But when we talk about safety critical applications, for example, self-driving cars or space applications or this aerospace applications, in all of those safety critical applications, even medical application and some industrial applications are very safety critical, right? In all of these safety critical applications, there are high reliability requirements. And as we know that our hardware is vulnerable, faults can occur in the hardware. And these faults compromise the system functionality by causing permanent damage or bit flips in the memory or in the computational elements. So in general, major goal for safety critical applications is that they have to fulfill AI application requirements because they are continuously varying. And on top of it, they have to also ensure reliability against faults, faults such as single event upsets, single event transients, aging, and multi-bit upsets as well. For example, if you take this example in a self-driving car scenario, in a fault-free execution of AI model or neural networks, your car will be detecting a truck, and in this case, brakes will be applied. But if there is a fault in the hardware and your neural networks detect a bird or misclassified to any other thing, then brakes may not be applied. And this is a very dangerous scenario. Such things leads to loss of human life and a lot of financial losses as well. Let's have a look at the shared layers approach. which is basically an efficient way of implementing multiple tasks on one single application specific accelerator. So let's have a look what happens in application specific accelerator niche. So generally, the focus has been on optimizing the hardware accelerator for one specific task. And also generally people are only considering, correlated tasks or tasks from the same modality. We term task as data sets, right? So we have three data sets. One is data set from the radar modality, FMCW radar hand gestures. Second is SVHN samples. You can also have a look at it here. These are the radar samples. And yeah, and this is a transformed MNIST. So this is the MNIST in which we have added noise to make it more difficult. And also we have made it three-dimensional because the original MNIST is 2D grayscale images. So yeah, we have added noise and we have also made it an RGB dataset. In a traditional scenario, for these three tasks, you would be using three different accelerator, and each accelerator will be optimized to process that specific task. And this is where, shared layers methodology for CNN accelerator comes into play. So let's understand what is the shared layers methodology for CNN accelerator. So the thing is, if you have a CNN network, the way it works is that in a CNN network, in a CNN model, the lower layers of the CNN learns the low level features of your image or of your input sample. And as you go deeper in the CNN network, the network starts to learn more abstract high level features. So it is definitely possible that different images or different patterns have similar low level features, but their high level features can be different, right? For example, in case of radar hand gestures and these FVHN data samples, these are totally different at the higher level. But at the lower level, because we are detecting edges and blobs and curves, so these low level features of most image patterns are same. And we have to apply this method towards our CNN accelerator now. So let's have a look how it works. So we have taken out all three tasks. One is from radar hand gesture, second is from SVHN data sample, and the third is from this transformed MNIST dataset. So instead of using three accelerator, we are using just one accelerator based on the principle that the lower level layers of this accelerator would be detecting low level features. And as you go deep in the network starts to classify high level abstract features. We are considering multiple tasks from different modalities. One is the radar modality and the other two are from the camera modalities. This approach is hardware efficient and power efficient because now we are using one accelerator to execute three tasks instead of the three accelerator. So I just would like to point out one more thing. When you are sharing the layers on the hardware, it means that you are sharing the hardware resources, reuse of weights. And this would also mean that, the weights of the accelerator, it knows all the three tasks. It has learned all the three tasks during the training process. So in this way, we don't have to save the weights for each different task separately. The same weights have already learned all three tasks, so they can execute these tasks in a time division multiplex manner. Basically, our approach also complements quantization and pruning strategies as well. So we have two different architectures, fused and branch CNN architecture based on shared layers methodology. So fused, we call this fused because in this all the layers are shared between all the tasks. Only the output layer has different classes corresponding to each task. In branch model is a model in which you have multiple branches corresponding to each task and subtask. Let's have a look at the branch architecture in a little bit more detail from the hardware perspective. So branch model consists of task-specific branches and it shares only particular layers. For example, task 3 is exiting earlier from the network, while the other tasks are going slightly deeper. And if you talk about from the FPGA point of view, we can have task-specific FPGA reconfiguration so that we can add or remove tasks based on our needs. We don't have to reconfigure the whole network, right? We can only focus on specific tasks. Selective replication of only specific layers, right? For example, if a certain task requires slightly higher reliability, you can do replication or you can do some hardware redundancy for only those specific task branches. And in this way, you can add more reliability for certain tasks. And another advantage is that you can have multiple subtasks as well. As I said, task 3 can be can detect digit as well and also color as well. As for example, in case of task 2, which is a more complex data set as compared to the task 1 and task 3, so we have added more number of layers and so that we can achieve the desired results for this task 2. So this figure here, this shows the whole workflow of the shared layers methodology, all the way from Python till the HDL generation. The first thing is data preprocessing. So the input data set should be transformed to suitable format before the model training. It has to be all the three data sets should be having at least the same input dimension so that it can be feed to the CNN model. So in data processing, we are doing transformation. We are also generating synthetic data for radars because for radar hand gesture, real data was less. So we had generated a lot of synthetic data as well. And that also helped us improve the accuracy of the radar hand gesture. Once you have the data pre-processing, you can create the model. We use TensorFlow framework. We have explored 5 different models. All of these models, TensorFlow models, are then fed to HLS for ML framework, where we specified our FPGA part number, interface, and some hardware parameters such as reuse factor and precision for the fixed point computation. And then it generates the Vivado HLS model, which then can be used to generate HDL model. And then at HDL level, you can perform synthesis and check hardware resource utilization and power consumption of these models. These are the implementation results. We have checked 5 different models: fuse model pruned, fuse model quantized. This model has both quantization and pruning as well. And then this is the branch model with quantization and pruning. We can have a look that in journal, we have achieved considerably good accuracy for all the 3 tasks. Instead of using 3 different models for 3 different tasks, we are using one model for 3 tasks, and we execute these tasks in a time division multiplex manner, right? When all the tasks are sharing all the layers, these are called fused models. And when there are branches, task specific branches, then it's called branch model. So there are a few results which you have to sort of have a look at. For example, latency. In fuse model, all the tasks have the same latency because all the tasks share all the layers, and each task is basically taking the same amount of time from the input to the output. But in branch, because each task is exiting the network from a different point, this is why each task has a different latency. This is in microsecond, by the way. The task which is exiting the earliest has the least amount of time. The task which is exiting at the end has the most latency. And this is the overall latency, which is the sum of all 3 latencies. In fuse model specifically, the more we are optimizing the model, the more power is decreasing, right? Because the hardware resource utilization is decreasing. This is the model. This is the most optimized fused model, which is quantized and pruned as well. And it has the least amount of power as compared to the other models. And also the hardware resource utilization of this FMQP model as well is less as compared to others. If you have a look at the accuracy results, branch models has slightly higher accuracy compared to the fuse model. And I explained the reason that because we are doing task specific training, so we are able to optimize, we have more control over training for each specific task as compared to the fused model. Well, in general, branch model is just offering slightly higher accuracy or latency advantages as compared to the fused model. For example, slightly higher accuracy here, slightly, for example, better latency. Previously, we had just one accelerator, slightly higher power consumption because we added more layers for each task. But it also offers reliability advantages as we discussed before, task isolation and all of those things. Our goal now that we for the shared critical application was, for example, to have a reliable processing. We were using different application specific so that we can sort of for different tasks. Trust we can instead use our system should be able to train all the three tasks together, include quantization and the pruning faults and just train one model. So we can create all the three tasks in a time division multiplex manner. And now in this way, one accelerator knows how to execute multiple tasks in multiple operating modes. This idea with three redundant accelerators. A reconfigurable CNN are being processed by all three accelerators. This would be termed as a fault. So let's have a look at it. For safety critical applications, reliability is very important. So we leverage the shared layers approach to propose a reconfigurable accelerator. We have three identical instances of the accelerator, and in those instances, different tasks can be executed in different operating modes. What are these operating modes? For example, one is the fault-tolerant mode, second is high-performance mode, and the third is de-stress or aging-aware mode. In fault-tolerant mode, all three tasks will be executed on all three accelerators. In this way, we will be having a TMR system which would be providing us high reliability for all the three tasks. In traditional approaches, where only one task is mapped on one application specific accelerator, in that scenario, implementing a TMR system would lead to 9 accelerators. While using the shared layers methodology, what we can do is we can use 3 accelerators to provide high reliability for 3 tasks. The other operating mode is high performance mode, or which is also called parallel execution of tasks. Let's say we don't require high reliability right now. Then we can, during the runtime, change the operating mode to high performance, and now each task will be processed by each accelerator, and this leads to 2x reduction in the latency. For example, if you remember, each task was taking 5.2 microsecond. Because this is a time division multiplex manner, these tasks are being executed. So the overall latency of the system is 15.63. But in high performance mode, in 5.21 microseconds, all the 3 tasks will be executed on all 3 accelerators, and then there will be a 2x reduction in the latency. The de-stress mode. De-stress is an aging reduction mode or a low power mode. Aging is inevitable. In de-stress mode, one accelerator is active at a given time, while the other 2 accelerators are switched off or put it in the idle position, or in other words, we put them in a stress-free configuration, which leads to reducing the aging. Because one accelerator already knows how to execute 3 tasks, so it can still be active. And in order to spread the aging across the different accelerators, we can switch between these accelerators in a round-robin fashion so that the aging is distributed evenly across the 3 accelerators. So in next video, we are going to be doing a comprehensive implementation analysis for all 3 operating modes. So yeah, let's summarize the presentation. In this presentation, we have discussed fused and branch models. We have discussed shared layers approach for multiple tasks from 2 different modalities and implemented on one application-specific CNN accelerator. We have discussed experimental results consisting of accuracy, power, hardware resource utilization, and latency as well. And then we extend this approach to propose reconfigurable CNN accelerator, which can perform in fault-tolerant, high-performance, and de-stress modes. What we are doing in our research group, we are on our way to make a fully reconfigurable or self-adaptive AI processing system consisting of on-chip sensors, quad-core RISC-V processors, reconfigurable AI accelerators, and reconfigurable hardware. And this shared layers approach and reconfigurable CNN accelerators are one of the important components of our this full reconfigurable AI processing system. And we will also discuss this thing later in the videos as well. So yeah, that's it from this video. Thank you so much for your time. So it takes a lot of effort to create these videos. So I would really request you guys to like the videos and subscribe to the channel. It will motivate us and we will continue to sort of make even more in-depth content like this. And additionally, if you would like to connect with me on LinkedIn, you can have a look at this QR code.